This week we're continuing to work with derivative applications. The first example here is just looking at whether a function is increasing or decreasing at a certain value, and we can also figure out the concavity at a certain value. So for increasing and decreasing, we need to take the first derivative, which is 12x squared minus 2x. And then to determine whether it's increasing or decreasing, we just evaluate the first derivative at that point. In this case, we get 14, which is positive, so therefore this function would be increasing at x equals 1. Sorry, x equals negative 1. Concavity, same idea, but we have to take the second derivative, which is 24x minus 2. We evaluate it at the point. We get negative 26. Because it's negative, we know it's concave down. Our second example this week, we're looking for some key points to a graph. So we're looking for the maximums, the minimums, and the inflection points. First thing I always do in one of these examples is take the first derivative and the second derivative. Now we need to find the max points, and to do this we set the first derivative equal to 0. This will give us two values in this example. We need to figure out whether they are a min or a max, and this is where the second derivative test comes into play. So we take these values and we plug them into the second derivative. And this tells us that the first one is a max and the second one is a min. We can also find the inflection points, or points of inflection, by setting the second derivative equal to 0, and this gives us x equals 0. Now all we need is to list all the points. So the max occurs at negative 0.577, 0.385. Point of inflection is 0, 0, and the min is 0.577, negative 0.385. Now all I did to find these was I take the x value and plug it back into the original function. So whatever the x value is, plug in the original function, and that will give you the y value. Our third example this week is optimization. Now this one here, we're trying to minimize the cost defense in this area. Now we know area is length times the width, and in this case we know it's 800 meters squared. We're going to rearrange to get y equals 800 over x. The cost of the fence, we have 3 of the small inside pieces of x, so let's label this x and y. So the x will be the width and the y will be the length. There's 3 that are going to cost $275. Plus 2 x's that are going to cost $325. Plus you get 2 y's that cost $325. Simplify this, you get 1475x plus 650y. We can now take our rearranged area and plug it in for y, so that we have an equation with only x's. At which point you can take the derivative we set the derivative equal to 0. We solve for x. Now in this case, we can rule out the negative because it doesn't make sense. We can use the second derivative test, which will give us 1.57 at x equals 18.78, so we know it's a min. From here we can find our y. Which is 42.60, so therefore the dimensions are 18.78 meters by 42.60 meters. Our last example is another optimization. This time we're working with a tin can. Now we're given the surface area, so 2 pi r squared plus 2 pi r h is equal to 2500. We're going to need to solve for h. Then we can start looking at the volume, which is pi r squared h, and we can plug in our rearranged h, so we get volume as a function of only r. We can simplify. Take the derivative. And just like last time, set the derivative equal to 0. R will equal to plus or minus the square root, 1250 over 3 pi, which is plus or minus 11.52. Again, the negative doesn't make sense, so we only have to look at the positive. You can do the second derivative test, and if you put 11.52 in for r in the second derivative, you'll get negative 217, so we know we have a max. We can take this r and plug it back into h. Which is 23.02. So we know the dimensions are a radius of 11.52 centimeters and a height of 23.02 centimeters.